Hello guys, welcome once more to another video in our revision series. Now this is the third objective of this topic and it states Newton's law of restitution. So what is Newton's law of restitution all about? So this law just states that the coefficient of restitution between two spheres when they collide, we call it E, is just equal to the velocity, or we can say the separation velocity divided by the approach velocity. Okay, that is what it is all about. Now the separation velocity is basically the difference between the final velocities of the spheres, while the approach velocity is the difference between the initial velocities of the spheres. So let me write it down. Separation velocity is equal to difference between final velocities of the spheres or the bodies, while the approach velocity is equal to the difference between the initial velocities of the spheres. All right, so I'm going to come back to the case we considered here. All right, so I'm just going to come back to this case, okay, and then we just analyze our coefficient of restitution using this case. So in this case, let me just put before impact and after impact. We see that the spheres had initial velocities of UA and UB, and then they had final velocities of VA and VB. So it therefore means that the separation velocity, so this is the scenario we are considering, okay. So we have this scenario where before impact, that is what is happening. We have the spheres are moving in that direction before impact. Then after impact, they acquire these final speeds of VA and VB. So we are going to use this scenario to state the Newton's law of restitution. All right, so if we want to state the Newton's law of restitution using this scenario, E, okay, will just be equal to, now follow very well, like we said, it is the separation velocity. That is, we have to take the difference between the final velocities of the spheres. So if I decide to take VA minus VB, all right, in the denominator I will try to exchange the positions of A and B. So in the denominator it is the approach velocity, and the approach velocity is the difference between their initial velocities. So if I begin with VA here in the numerator, in the denominator I will begin with UB, alright, then minus UA. But if I decide to begin with VB, so I'm just going to write it is the same as, if I decide to begin with VB in the numerator, I'll do VB minus VA, but when I go to the denominator I will begin with UA, alright, so UA minus UB. Now for me, maybe not to be confused, for example, if I have not mastered this and I just want to have VA and VB and then UA and UB, I'm going to attach a negative sign to E. Alright, so any way you state it, we can put negative E is equal to, if I do VA minus VB, then I'll also do UA minus UB, because I've attached a negative sign to E. So master any of them, alright, but I usually just work with this one, alright, that's my favorite. I usually work either with this one or with this one. I always run away from the negative sign because I can forget it. Alright, so this is basically the Newton's law of restitution. Now when I ended the previous video, I said that, let's go back to it, I said that if the coefficient of restitution is 1, the collision is elastic or perfectly elastic. Generally, collisions are always inelastic, all right, and E is always between 0 and 1. And if it is now perfectly inelastic, E is equal to 0. Now we should also know that in elastic collisions, the momentum is conserved and the kinetic energy is conserved. So in this guy we have momentum. It's not only kinetic, it's only momentum that is conserved. Momentum and kinetic energy are both conserved. Now in this guy, since E is 0, none of them is momentum is conserved, but kinetic energy is not conserved. Sorry, for inelastic momentum is conserved, but Ke is not. All right, and then for perfectly inelastic, Ke no momentum, none of them are conserved. All right, so most at times we just dwell on the first case and the second case, but most at times we are always going to be giving questions on the second case. Okay, but I'm going to give you guys a little example on the first case so that we actually see what is happening. All right, so our first exercise or our first example is that consider two identical masses A and B of mass m. No, consider two identical spheres A and B of mass m. Okay, now A is moving with a speed of u meters per second towards B, which is stationary. All right, so initially the speed of u is a meters per second. The direction is towards B, so the velocity still remains positive. But if I give you that the speed is u meters per second away from B, then your velocity will be negative u because the direction is pointing to the left. All right, so B is stationary. Now if the collision is elastic, show that there is an exchange of velocities. Now when they say there is an exchange of velocities, means that the initial velocity of A becomes the final velocity of B, and the initial velocity of B becomes the final velocity of A. Now let's highlight our key terms. Identical is the first thing. The next thing is the speed of A. Okay, the next thing is that B was stationary, and the next thing is that the collision is elastic. So we are going to use this to solve the problem. Okay, so no need to redraw the diagram again. All right, we are just going to apply the principle of conservation of linear momentum. I'm not going to write down all of that long stuff, but please always write it down. So from the principle of conservation of linear momentum, the momentum before collision equal to the momentum after collision. So the mass of A is m, the initial velocity of A is u because it is moving towards B. We are assuming that it was moving to the right, and going to the right we conventionally say you are moving in the positive direction, plus the mass of B is also m because A and B are identical spheres. The initial velocity of B is 0 because initially it was stationary, that is, it was at rest, equal to the mass of A after impact does not change, is still m. The final velocity of A after impact, we can call it VA, plus the mass of B after impact is m, and its final velocity is VB. Now we realize that m is common. M, in fact this is even 0, so this m here, okay, we cancel off with this m, we cancel off with this m. Doing that, we are going to have that VA plus VB is equal to u. That is our first equation. Now we are going to apply, so let me just write beside here, principle of conservation of linear momentum. Okay, that's the application. Now the next law we are going to apply is the Newton's law of restitution. Okay, now this Newton's law of restitution is telling us that the coefficient of restitution between the spheres is the ratio between the velocity of separation, which is, if I take VA minus VB, I'll divide with what? UB minus UA. Now my UB is 0 because B was at rest initially, and my UA is just U. My numerator, I have VA minus VB. Okay, from there I'll just multiply both sides by this negative U. Okay, and then what I'm going to have is that VA minus VB is equal to negative E times U. But since the collision is elastic, your E is equal to 1. Alright, so which is going to give me negative U. We can call this equation 2. Now objective is to find VA and VB at the end of the day. So we can just solve these two simultaneous equations by elimination. If I take equation 1 plus equation 2, you see that VA will add up with VA to give us 2VA. Okay, now VB will add up with negative VB to give us 0. U will add up with negative U to also give us 0. So 2VA is equal to 0, which means that your VA is equal to 0. You see that VA is now 0, and this 0 was actually the initial velocity of B. So there is an exchange of velocity. Now if we subtract the two equations, 1 minus 2, what we are going to have is that VA will cancel off with VA. VB minus negative VB is basically 2VB, okay, equal to U minus negative U is 2U. Alright, so from here we divide both sides by 2, and VB gives us U meters per second. You see that the final velocity of B is now the initial velocity of A, so there is an exchange of velocity. Alright, so let me see how long the video is. Already 12 minutes. Let me take it to 15 minutes. Alright, so even to 20 minutes, because we have a lot to do under this. Now there is a peculiar case again when it concerns the Newton's law of restitution. Now we have just been seeing collision between two spheres. Alright, now let us see collision between a sphere and a wall. Okay, let's analyze that case. So let's talk about collision between sphere and wall. So the collision between a sphere and a wall, we are going to analyze it, and you see. Okay, so let us suppose that we have a sphere A, so let us suppose that we have a sphere A. Now this sphere is moving towards a stationary wall. Bon, the wall cannot move, right? So there's no even need to call it stationary. So this sphere is moving towards this wall. Okay, so the sphere is moving towards this wall. Alright, so the wall is actually vertical, and the sphere is moving in the horizontal, in a direction perpendicular to the wall. So this sphere is moving towards this wall. So this is actually before impact. Now at impact, what happens is that there is normally impulse, right, exerted by the sphere on the wall. Sorry, exerted by the sphere on the wall, yes, and by the wall on the sphere. But that exerted by the sphere on the wall is very negligible. Alright, so the main impulse is actually the impulse that is exerted by the wall on the sphere. So the impulse experienced by the sphere is going to be pointing in this direction. So the impulse exerted by the sphere, the impulse experienced by the sphere, we call it JA. So this is at impact. Now after impact, the sphere rebounds. So the sphere is now going to be moving. So the sphere has now left the wall. It is now maybe somewhere here. Alright, so the sphere actually acquires a final speed or a final velocity. We can call it VA. Alright, we can call it VA. Voila, so this is impact between the sphere. Now the coefficient of restitution also exists. Okay, the coefficient of restitution between the sphere and the wall also exists, and it has its own value. Sometimes it's given to you in the equation, sometimes you're asked to find it, maybe using some other informations. Let me just take this man to the next slide. Okay, so the objective is we are going to determine the final speed, the final velocity of A after colliding with the wall. Alright, so this is a very important application of the Newton's law of restitution. Now dear students, you guys have to take note that when we are dealing with a sphere and a wall, we don't consider the principle of conservation of linear momentum. This is because this wall has a very large mass that we don't need to even think about its value. Alright, so in essence, we always consider only the principle that talks about the Newton's law of restitution. Now, by the definition of the Newton's law of restitution, it says that the coefficient of restitution between the two colliding bodies is equal to velocity of separation. Like I said, I always like to begin with my sphere, VA, minus V wall, alright, divided by U wall. You guys should remember that we have to exchange U wall minus UA. Okay, now this is velocity and not speed, so we have to take into consideration the direction. Now let us look at this. So actually, okay, let's come back here. This VA is the velocity. It is pointing in which direction? It is pointing to the left, so it therefore means that we have to attach a negative sign to it. This negative sign is indicating that it is pointing to the left, and this VA value itself is just the speed. Alright, so the value VA is just the speed, but now the sign that is attached to it indicates the direction of that speed. Automatically we now call it velocity. But in cases where we are just moving to the right, the velocity is definitely the speed, because the direction is in the positive direction. Alright, your V wall is 0, okay, because the wall does not shake before and after impact. So we are going to have negative VA divided by negative VA actually minus 0 divided by U wall is also 0 because initially the wall is at rest, then minus UA. Be mindful about this negative sign there is originally in the formula. Alright, why this UA here is positive? Because it was moving to the right. But I attach a negative sign to this VA here because this VA here is just the speed. Alright, but the speed is in the opposite direction. That is why we have a negative sign attached to it. Now if we simplify, we are just going to have negative VA divided by negative UA. Okay, the negative sign cancel and we are going to have VA divided by UA, which therefore means that after a body collides with a wall, the final speed or the final velocity it acquires is just given by the coefficient of restitution between the sphere and the wall times the velocity that the sphere used to move to the wall. Because if I just take this E times UA, I'm going to have VA. So take your time to really analyze and understand this. So it's very important to know that when you're colliding with a wall, we consider only Newton's law of restitution. We don't take into account the principle of conservation of linear momentum, because the wall is not mobile. Okay, the wall stays at rest before and after impact, so we don't consider the principle of conservation of linear momentum. All right, so I think for this video I'm going to end here. All right, this already 20 minutes like I supposed. Now let's see what we are going to do in our next video. So we are done with objective 1, objective 2, objective 3. In objective 4, which is our next video, we are now going to be solving problems properly. We are going to look at direct collision and impact between two spheres. Okay, then so actually these practice exercises will also fall under number 4. Okay, before now, in the second to the last video, we look at KE loss and KE gain due to impact. All right guys, if you have a question, make sure you ask in the comment section of this video, or in this website, or in our WhatsApp channel. Thank you guys for watching. Remain blessed and see you guys in the next video.